Into our second topic of the second half, looking at aggression, competition, cooperation, empathy, all those guys, and we've got the drill down by now, starting with behavior all the way to the right, working our way to the left, all the way back to evolution, genetics, blah, blah. Where we left off the other day was just getting into the first box worth of what's going on in the brain. What is the neurobiology of what's occurring seconds before that aggressive act, that compassionate act, all of that, as we know already, right in the middle of the limbic system, of course. As we know already, the amygdala is playing a really central role and seeing all the evidence for it, lesion studies, stimulation studies, the bizarre, rare realm of humans who have had lesions or stimulation there, accidents or intentional psychosurgical interventions, beginning to look at the amygdala there and the role that it plays. Now, part of what becomes relevant there is seeing the kind of information that the amygdala is getting. And an important thing to focus on is something that was mentioned back in the limbic lecture, the notion we ended with the other day, the amygdala. Okay, so you look at somebody who has had amygdaloid damage and they tend to not be able to detect fear-evoking faces. They are overly trustful. They are underly skeptical. They are not taking in the sort of information we would that leads us to conclude this is a circumstance that demands arousal, vigilance, so on. One of the things that was seen, interesting study that I noted at the end the other day, was looking at people with amygdaloid lesions, Damasio and his group looking at this, keeping track of where the eyes are looking. When they see another face, they are not looking at the eyes anywhere near as much as everybody else would. They're instead tracking around all sorts of extraneous parts of the face. Normally people look at the eyes a whole lot. And what that winds up showing is not only is the amygdala playing a role in deciding this is a fear or aggression evoking stimulus, the amygdala is also on the lookout for it. And what we will see in a little while is one of the things testosterone does is make the amygdala better at looking for fear and anger evoking faces. So part of what the amygdala is doing is taking in sensory information. We touched in the limbic lecture on one interesting aspect of it. Okay, back to that business, that the limbic strategy of counting the number of synapses, that strange business about olfaction being only one synapse away from lots of parts of the limbic system, including the amygdala. If you were dealing with a rhinoencephalon, the olfactory world is being so emotional for a rodent. For us, we've got something else interesting happening. And I think I mentioned this. Okay, so you got the visual system, and what we have is the usual rule that visual information, just like auditory, just like tactile, comes in and goes by way of a way station along the way, whose name we won't worry about, and goes through all these levels of cortical processing, and BioCore people will remember layer 1, doing dots to lines to moving lines, all of that, eventually processing, assessment, come up with an idea that, oh dear, this is a menacing face, and then let the amygdala know about this. What was also found a number of years ago is that there is a shortcut, there is a branch coming off of this way station called the lateral geniculate. There's a branch coming off which then is only one synapse away from the amygdala. What we heard is that's really useful in that it can get you fear-evoking, arousing information that much faster than going through all this cortical processing. It is a shortcut. It is not one synapse away, but it certainly makes for fewer synapses. That's a faster system that we've got in order to very quickly pick up information that should be of interest to the amygdala and all of its fear, anxiety, aggression type concerns. So that's wonderful. That's terrific for the amygdala. What I think we also heard is it comes with a downside, which is you send all this information through all these different steps there because it's doing all this cortical processing for you. It's figuring out all the details of the sensory information you're getting in. This way, it gets to the amygdala faster, but what gets there is less accurate. you're more likely to make a mistake. And that's the whole world of people reacting really quickly to some peripheral piece of information, which turns out to be different than they thought it was, and before they knew it, they had reacted. This is the cortex sitting there still trying to decide, is this a three-dimensional object or a two-dimensional one? And through this route, you've already stabbed the individual. This is a very, very clear trade-off: faster information, less accurate. And there's by now a lot of evidence to suggest that this particular pathway is hyperexcitable in individuals with post-traumatic stress disorder, where that whole world of all sorts of acute sensory stimuli suddenly fling the person back into where they were when that happened to them, and without the processing time to figure out, this isn't exactly the same. In fact, this is a world away from where that happened. Already the amygdala is responding. So these shortcuts, but telling you one of the things you give up with the shortcuts is the analytical accuracy. Okay, so amygdala for that. Amygdala equals fear, equals anxiety, equals aggression. Isn't that interesting? In a world in which amygdaloids are not afraid, there's no aggression, that whole theme there. The amygdala isn't always about fear and aggression and anxiety. And it's very informative, the examples where that's not the case. One case, really interesting syndrome called Williams syndrome, which we're going to hear a lot about in the language lecture. Williams syndrome appears to be a poorly understood imprinted genetic disorder where you get, among other things, kids who are unbelievably facile with language and emotional expressivity. This whole world of Williams kids, it's this fascinating disorder where you get kids who are basically borderline retarded in terms of cognitive function, yet they have this spectacular adeptness at language, at reading emotions in other people, at communicating them. They are famously affectionate kids amid being very cognitively impaired. We'll see in the language lecture, most people think about Williams syndrome as an interesting example of the modularity of language control in the cortex. You can have very, very sort of facile language skills in these individuals who nonetheless are typically in the IQ range of about 70, argument being, we'll see in a couple of weeks, that there are specialized cortical areas for language. For our purposes, the interesting thing about Williams kids, and eventually Williams adults, is they are extremely trustful. They are extremely gregarious. They are incredibly vulnerable as adults to being taken advantage of by other people. And what you see with Williams individuals is you basically cannot evoke amygdaloid activation with scary faces. They don't register in someone with Williams. So there we see that this is not universally serving that role. Another example where there seems to be an exception, until you think about it a little bit, people with social phobias. What studies have shown is, show a social phobic any sort of face, human face, and their amygdala activates. Oh, that's not telling us anything informative. It's telling us something very informative, which is, if you have a severe social phobia, any face is a scary face to you. All faces do that, rather than only ones communicating certain threatening emotions. Another one that seems puzzling, but which then makes perfect sense when you think about it, when you take people with clinical depression, the amygdala doesn't necessarily activate when you show them a picture of something frightening. It activates when you show them a picture of something sad. Okay, so now instead of doing fear and depression, the amygdala does sadness or something. If you think about it for a minute, that makes perfect sense. What the amygdala might very well be doing is responding to whatever it is that is most ethologically frightening to you, you as a species, you as an individual. If you are somebody who's depressed, the most frightening thing on earth is something sad around you as more justification for feeling even more depressed. The amygdala being far more subtle than, ooh, here's a scary predator with a knife coming at me, very much contextual. Okay, another thing that the amygdala is brilliant at, which we will come back to in more detail, but on a first pass is so depressing, is the amygdala is probably the part of your brain that is best at doing dichotomizing between us and them, forming categories in-group, out-group, and responding to out-group stimuli. And we will see two things down the line, probably on Friday. Number one, it is really depressing how readily the amygdala forms some of these us-them dichotomies and the sort of thems that it responds to. Really depressing, but also some good news in there, remarkably subtle social manipulations that will change the sort of us-them dichotomies that the amygdala responds to. So stay tuned for that. Okay, so shifting from the amygdala, going to the incredibly interesting, important frontal cortex. And frontal cortex obviously was doing all sorts of stuff 2 lectures ago in the sex lecture, getting you to have the appropriate context for sexual behavior, getting to do the harder thing like leaping over streams and headbutting with other antlered beasts, if that's part of your mating season. Where the frontal cortex is particularly involved is this whole world of regulating appropriate behavior in the context of violence, aggression, competition, cooperation. Frontal cortex is incredibly important here. Okay, back to the limbic lecture. The limbic system is about subcortical structures underneath, things like that, and the cortex is about the cortex, and we heard in the limbic lecture, instead what was originally that heretical view by that neuroanatomist Nauta saying, actually the frontal cortex is part of the limbic system. It should be viewed as such, and over the years since, it being viewed as this is the cortical part of the limbic system. This is the cortical region that is intensely involved with limbic function, with emotional function. On an anatomical level, what we've already seen is, just as a first pass, tons of bidirectional connections, everything in the limbic system talking to the frontal cortex sending projections back all over the limbic system, so anatomically it's there. So in terms of what it's doing, the best way to describe what the frontal cortex is about is when there's a choice between doing something harder and something easier, and the harder thing is the better thing to do, it's the thing that makes you do the harder thing. And we'll see this plays out in all sorts of domains. The frontal cortex getting you to do the harder thing. First, beginning to see the way it works in terms of wiring. Okay, here we have reduced the entire world down to a simplified, there's 2 neurons that account for all the easier things you do in your life, and there's 3 neurons that account for all the harder ones. Here we have some circumstance where there's a circuit at some juncture, the easier but less desirable outcome. Behavior is this way, the harder one that way, and what you see is this has more inputs than this one. This is obviously some entire circuit of neurons, and this is highly simplified, blah, blah. But what we see is the way it's set up here is that there are more inputs into this pathway. This is what makes this neuron easier to activate than this one. There are stronger inputs into this pathway. This one has only 2 axons going to it. This one has 3. Yes, simplified. When you look at the wiring of the frontal cortex, it's sending projections all over the limbic system, all over motor areas. A characteristic of the projections is that very rarely are they very strong projections to any given target area. They're not the sort of projections where here's this limbic, this frontal cortical neuron that is now dumping all of its axon terminals into this one neuron down there. It does not exert a very strong influence over the excitation of any given neuron. Instead, what it has is a whole lot of weak but diffuse projections. What is the frontal cortex doing? It's slowly massaging the area there. It is giving biasing bits of depolarization of excitation. So what we've got here is, okay, the numbers are not quite working, but in any case, what we have here is, here's doing the right thing, that's harder, and it's a lot harder to get this neuron to do the right thing, that's harder, because there's less of an input than this pathway. What the frontal cortex tends to do is have these relatively weak inputs into all these systems where it makes it a little bit harder to just fall for this one. It gives more strength into this pathway. The frontal projections very rarely are active activating on their own, yes, indeed, we have another example here of modulating if and only if this pathway is already struggling to do the right thing. The frontal cortex tends to be able to push it over the top there to pull it off. Frontal projections as very diffuse, relatively weak, but biasing towards excitation rather than causing it, that tends to be the thing that it does. Okay, what you see in terms of making sense of frontal function is, as we heard the other day also, a huge whopping projection from that nucleus accumbens. You remember ventral tegmentum, nucleus accumbens, this huge dopaminergic, dopamine releasing projection into there. And on a certain level, you want a totally useless metaphor, but on a certain level, what the dopamine projection is about is, so here you've got the frontal cortex. The frontal cortex for a living makes you do the harder thing when it's the right thing to do. Dopamine is, in a sense, the fuel for that activity. Dopamine, the expectation, the anticipation, the capacity of dopamine to generate goal-directed behaviors is heavily running through this pathway. Dopamine is the thing that's giving, in a sense, the frontal cortex the energy to just push you over the edge and to tell you, yes, go this way instead of this way. What's also intrinsic in this is lots and lots of frontal projections that are inhibitory in that realm. An awful lot of what frontal cortex is also doing is whispering to this pathway saying, you really shouldn't do that, you're going to regret it, I know it's tempting right now, don't do it, don't do it. This super ego sort of neuroanatomy there of frontal cortex, dopamine as very strongly stimulatory in there. The whole role of dopamine as driving goal-directed behavior. And that was like critical business we saw in that study, showing you let the monkey know that it's now entered one of those periods where if it lever presses, it gets the reward. Ooh, I know just how this works. Anticipation, that's great. Up goes dopamine. If you prevent the dopamine from going up, you don't get the lever pressing. Dopamine is not just about anticipation. Dopamine is about driving the behavior needed to get the reward that you are anticipating. Dopamine as goal-directed behavior. Okay, so what you begin to see in terms of how this frontal cortex does this making you do the harder thing, it's manifest in all sorts of domains. Easiest, most accessible realm is seeing what it has to do with cognition, the way in which the frontal cortex gets you to do the harder thing. What it helps you to do is organize bits of information in ways that makes it easier to make sense of. Here is, if you ever find yourself being borderline demented and somebody's giving you a test, this is one of the tests they're going to give you, so start preparing. And this is this horrifying test called the CVLT, the California Verbal Learning Test, or some such thing like that. But here's what they do. Some neuropsychologist sits you down and says, oh, I'm just going to tell you something, a list of things here, see if you could remember. Today I went to the market and I bought 1 tomato, 1 hammer, 1 box of cereal, 1 grape, and goes through a list of 16 of these, one every second or so, and they finish and they say, okay, do you happen to remember what I bought at the market today? Oh my God, it is so stressful. So you manage to get out like maybe 7 of them correct, and the person says, okay, that's very good, let's do that again. Today I went to the market and I bought 1 tomato, 1 hammer, 1 box of Cheerios, 1 box of Star, and goes through this list again and seeing each time how many of them you remember, beginning to see your memory acquisition thing as you're getting closer and closer to remembering all 16. It's not until you're maybe in the 3rd or 4th round of doing this that you begin to notice something, which is of the 16 items, 4 of them are fruits, 4 of them are hardware items, 4 of them are bread cereal things, 4 of them are who knows what, and they're scattered throughout. What the people typically start doing by the 3rd or 4th one is you begin to group them by categories. And instead of remembering back, okay, tomato, hammer, cereal, fruit, whatever, you first tell the 3 out of the 4 fruits that you remember. Then you tell the the 2 out of the 4 hardware items, you're beginning to group the information. And what that is called is executive function. Executive organizing strategy, it is sheer memory systems that are remembering sort of these 16 factoids. It is executive organizing that's telling you, do you notice some patterns there? Don't just remember it in sequence. Don't try to just remember it in sequence. Stop for a second and try to keep track of the categories, because that's going to be a better strategy in the long run. That's what the frontal cortex does. You get someone with frontal cortical damage, and their capacity to remember, the learning curve is not all that different from anyone else, but they never start doing the grouping. They never start doing what we might think of as almost cognitive strategizing. Ooh, I see a pattern here, and I suspect if I put the effort into exploiting that pattern, it's going to make it more productive for me to try to remember things rather than just trying to do it in sequence. So the frontal cortex is good for that. Where else do you get in the cognitive realm the frontal cortex getting you to do the harder thing? Where you get all this information in the cognitive realm is when you study people with frontal damage. Either people with accidents, or very often older individuals who have strokes there. There's a very distinctive type of dementia that takes out the frontal cortex called frontal temporal dementia, and all sorts of cognitive tests in those cases showing in the cognitive realm what happens when you're not having this going on throughout all the circuitry. One thing that would be given, okay, so you sit down this individual and you say, okay, you recognize this, don't you? Even though most of you guys don't by now, growing up in the digital era, but this is the face of a clock, and it comes with a little hand and a big hand, and they point in informative directions. So you ask the person, okay, you recognize this, of course, this is a clock face. Now, where would you draw the hands if I said the time was 11:10? 11:10, so sit for a minute and think about where we're going. Of course, it's 10 minutes after 11, and that's where the hands would go. Someone with frontal damage instead would draw the hands at 11 and 10. What are the rest of us doing? We're saying, okay, the easier thing is to just get gummed up on the number 11 and the number 10. Wait, don't do that. Hold on. Remember, 10 is a coding for multiples of 5 minutes, because that's the way clocks are organized. So 10 is actually 2 of these, so it's 11, 10. 10 is a shorthand for saying 10 minutes after 2, and you put your hands in the right place. Somebody with frontal damage can't hold off, and they get pulled by the easiest interpretation of the sound 11:10. They draw the hands at 11 and 10. So this is what you would see. More examples. What the frontal cortex is good at is getting you to inhibit the easier route when it is a very well-learned, very well-conditioned one. Here's what you would do. Now you take the person who you think may have some frontal damage, and you say, okay, here's a task I want you to do. Starting with December, tell me the months of the year backwards. What have we all learned since way back in first grade or whatever, that this is an easy thing going forward, this is the harder thing right now. And you will see a person with frontal damage will say, okay, December, November, October, September, October, November, December. They manage to pull it off for a while, and then they just slip on the ice back into the easier way. It is, you normally have December followed by January, not by November. It takes more work to do it that way. People with frontal damage, they have this intrusion. They can't hold off the overlearned response, the more habitual response. You would then see, with frontal damage, something that's termed intrusions. Now you would say to the same person, okay, that's great, that's great. Now what I want you to do is start with the number 20 and count backwards. And the person will say, okay, 20, 19, 18, 17, September, October, November, December. And they've slipped back into the previous task. They don't have the effort here to say, we've stopped it with the months already, now we're doing numbers. Don't slip back into that month stuff, but yet that's exactly what occurs. You take somebody with frontal damage, you give them what would be called a verbal fluency test. You say, okay, 1 minute, tell me as many words as you could think of starting with the letter F. Great. Now tell me as many words as you could think of starting with the letter M, with the letter P, so on, and you go with letter M, and by the fifth word, they're back to words with F. The previous task intrudes in there. It has trouble organizing, strategizing. We're done with the letter F. We're done with doing the months. Concentrate now. We're doing the letter M. We're doing numbers backwards. Don't fall for the easy version of just saying 11, 10. This is the stuff that the frontal cortex does. This is what it looks like when you are getting damage to the frontal cortex. Okay, so cognitive aspects of that. What's the frontal cortex particularly good at in the cognitive realm? It is making you work and work and work for a cognitive reward way down the line, and that's the entire world of all of you guys already gunning for the perfect GPA that will get you into a good nursing home someday. That is your frontal cortex working to your advantage. That's your frontal cortex doing that, this task of gratification postponement. Do the harder thing. Where am I going to get the energy for it? It's these frontal inputs that's just biasing so I could do the harder pathway rather than the easier. You find this also when you're doing electrophysiological, when you're recording, you're sticking in electrodes and seeing when neurons are excited. Suppose, for example, you've got a monkey and you are recording, you have electrodes both in the visual cortex and some other ones in the frontal cortex. And again, this is one of those tasks where when the bell sounds, bells don't beep, when some buzzer beeps, it means to the monkey now, okay, every time the light goes on, you have to press a lever 3 times and you get a reward. That's the rule. Buzzer means we're starting one of those testing sessions again. Light comes on, hit lever, light comes on, hit lever. So you record from the visual cortex, and here's what's happening. This is when the buzzer comes on saying, oh, we've just started one of these test periods, and now the light flashes and the visual cortex activates each time. What's going on in the frontal cortex? The second the buzzer goes off, the frontal cortex activates and it stays up the whole time. What is the visual cortex coding for? Individual examples of this task. What's the frontal cortex coding for? It's remembering the rule. Okay, the buzzer went on. That means now remember, remember, remember for the next whatever period of time. Get ready. Every time a light flashes, hit the lever there. The task of the frontal cortex is to maintain the rule throughout, transcending the individual examples of it. So you can already see where we're heading with moral development in kids and frontal maturation, and all of that's going to fit in really well. The frontal cortex doing stuff like that. What you should begin to notice is intrinsic in all of this, the frontal cortex is sending these projections all over the brain. The frontal cortex does not code for individual examples of rules, but instead maintains rules for long, long periods. The frontal cortex works really hard. Frontal cortical neurons have very high metabolic rates, and a whole world of neurology thus is built around the fact that frontal cortical neurons are very fragile. They die very readily. All sorts of neurological disorders damage the frontal cortex with behavioral changes that go along with that. Okay, so you've got the wiring, the patterning, all of that, but then at some point you wonder, well, and learn all sorts of rules. Back when I was about 3 years old, I learned this rule having to do with, no more diapers, and if you go to the potty, you get M&Ms, and in fact, I sort of have internalized this, and does that mean you need to go to the bathroom now, is internalized that there's a frontal cortical neuron that got excited when I was 3 years old and got toilet trained and has been firing ever since then? No. What you see after a while is the frontal cortical realm of remember, you go to the bathroom when you need to do this, remember, you say the months forward, remember all these sorts of things. At some point it becomes automatic. It becomes reflexive. And what is seen is, at that point, the frontal cortex stops being the area that is active. At some point, instead, it becomes implicit pathways, procedural pathways. It gets stored elsewhere in the brain. What you see in individuals with Alzheimer's disease, where you get a lot of damage to the hippocampus and the cortex, particularly the frontal cortex, what you see is all sorts of things that were learned way back when and learned enough to just be habitual, people can still do. You will have somebody who is demented enough that they could not tell you what decade it is, the name of their spouse, the name of their children, how many children they have, whatever, but this is someone who still knows how to knit. They learned when they were 7 years old how to knit, and now 80 years later they can still do that. This is not the frontal cortex remembering the knitting rules for the last 70 years or so. This is, it became automatic and got moved elsewhere. And a whole bizarre world you see with frontal damage in individuals with these dementias, where some of the things that become automatic are remarkable, suggesting that you've got storage capacity in other places in the brain when you don't have to consciously think about it. When something has become so automatic, you go to the bathroom when you need to void your bladder. Okay, we don't have to think about that anymore. It has now gotten to a pathway like this. Other brain regions, particularly the cerebellum, seems to play a large role in that. Stay tuned. We are going to be getting to a very interesting point about moral development in kids. When do certain moral rules stop having to be coded in the frontal cortex and instead become as habitual as toilet training? We'll see some really interesting implications of that. Okay, so what do you see when you get frontal damage? You get all these cognitive problems there, and these problems with doing the harder but more correct thing cognitively. You see it as well in terms of doing the harder but more correct thing in terms of behavior, social behavior. First classic example of this, they take away your neurobiology license if you don't mention this guy at some point. How many of you have heard of Phineas Gage? Okay, how many of you have not heard of Phineas Gage? Okay, time for Phineas Gage. Okay, but the ones who have heard of him, let's all say this in unison. Okay, Phineas Gage was the first identified individual to have massive frontal damage. Phineas Gage was a foreman on a railroad construction line in Vermont in the 1840s. One day, thanks to somebody or other doing something wrong, there was an explosion of some dynamite which blew a large metal rod through his forehead and out the other side, taking out his frontal cortex in the process. And this was rather dramatic, and this was this large metal pole that went through fast enough that in fact cauterized all the blood vessels. And you can go see that metal pole at the museum in the Harvard Med School library, where you can also see his skull, which is very interesting because the rest of Phineas Gage is about 20 miles from here, buried in Colma, so I don't quite know how his skull wound up at that end of the country, but in either case, he was buried in San Francisco minus, well, I guess the dean of Harvard Med School swooped in, and before you knew it, the skull was on its way east there with the metal rod. But in any case, okay, so Phineas Gage had his frontal cortex splattered 15 feet behind him, and what happened was, amazingly, because it went through with such force and so fast that it cauterized all the blood vessels, he was actually able to get up at that point. And most remarkably, with a bunch of people from work, he was able to walk 1.5 miles to the nearest doctor, who, being a good diagnostician, took a look at Phineas Gage and tilted his head back and looked at him and he said, "Whoa, you got a hole there in your head." And was sort of looking in more detail and saying, "Whoa, you've got frontal cortex got blown out of your head there." And this was sort of the peak of diagnostic skills at the time. But what happened was the boss there on the railroad line said, "Gage, you know what? Take the rest of the day off. See you tomorrow." So Gage goes home, and the next day he returns, not just figuratively, but literally transformed overnight. Gage, who was this sober, sobrietous, religious man, highly reliable, foreman of this entire workplace, etc., Gage was never able to work a day steadily for the rest of his life. He became this brawling, abusive, sexually predatory, out-of-control individual, and that original doctor, seeing what he turned into, was the first one who said, well, whatever that part of the brain was that got taken out there, whatever it was, that part of the brain reins in our animal energies. And 170 years later, there's not a hugely better definition out there as to what the frontal cortex is about. So Phineas Gage being the official first one, and you learn all about this guy, but very interestingly, about a year ago, somebody found the very first photograph of Phineas Gage, and go look at that online. What's interesting is he looks like a perfectly normal guy. The pole took out his eye along with the frontal cortex, and obviously there was that problem. But this is like the face of somebody from the 1850s, and there's something, I don't know, I found very moving about seeing this face, that everybody learns about Phineas Gage, and everybody has seen his skull and the reconstruction of the accident, and That's right. This was like a regular old person whose life was completely destroyed when the frontal cortex got scattered all behind him there. Remarkable first example of that. Since then, most of the evidence for what frontal cortex is about from damage is older individuals who have stroke damage to the frontal cortex. And what I mentioned, I think, in the limbic lecture, one example of what this looks like was a horrifying case in a facility in the East Bay some years ago where an 80-year-old man who had had extensive frontal damage due to a stroke was found to have raped an 80-year-old woman with Alzheimer's disease. This is what frontal damage looks like in an 80-year-old. Here's something very interesting to consider, and seeing exactly the terrain we're heading into here with this sort of information. Approximately 25% of men on death row in this country have a history of concussive head trauma to the front of their head. Front of the head, where you wind up damaging the front of the brain, frontal cortical damage. And what we enter into here is this whole realm where this stuff is stupefyingly relevant to making sense of criminal behavior in humans. Possibilities of frontal damage. Currently, there is one law that's on the books in the majority of states in this country for deciding when somebody is so organically impaired that they count as having an insanity defense rather than being criminally culpable for their acts. And this is something called the McNaughton Rule. McNaughton Rule, everybody gets taught that what the McNaughton Rule is can the individual tell the difference between right and wrong? This is the gold standard in courts as to whether or not somebody gets a organically impaired insanity defense ruling or not. McNaughton, whose work, that was all of this cutting-edge neurobiology was based on, McNaughton was most probably a paranoid schizophrenic, a guy in 1840 who attempted to assassinate the Prime Minister of England and was so clearly psychotic that this was the first case of a jury formally saying that no, there is something too sick about this man to hold him responsible for his acts. And the clearest thing that came through in that trial was he could not distinguish right from wrong. And the sort of thing that absolutely does in somebody attempting a McNaughton defense in a criminal trial is if there's evidence that they tried to cover their tracks afterward, that they were aware that they had done something which was unacceptable. What you see with people who can't tell the difference between right and wrong, there's no evidence of them trying to cover up their tracks. Where do you see McNaughton rules standardly applied? Severe schizophrenics. And for example, John Hinckley, the person who tried to assassinate Reagan in the 1940s, in the 1980s, but well, I won't go there, but in the 1980s, and he was found innocent or guilty with an insanity defense because he failed a McNaughton ruling, severe schizophrenic. So this has been the gold standard in most of the courts in most of the states in this country. The only way you could be held not accountable for your criminal actions because of organic impairment would be if you can't tell the difference between right and wrong. But then you got a problem, because you get people with frontal cortical damage, and they can tell the difference between right and wrong. They know the rules, they can state them for you, yet they can't control their behaviors. And this comes through with all sorts of tests, but you could show this now with people with frontal damage. And for example, here's the M&M test that you give them, and what you've got is something desirable. In this hand you have 5 M&Ms, in this hand you have 1. And the rule is, if the person reaches for the 5 M&Ms, you pull your hand away quickly and they get 1 M&M as a reward. If they reach for the 1 M&M, you pull your hand away and you give them 5 M&Ms. In other words, can they be disciplined enough to not reach for the 5 M&Ms and instead hold out and go for 1? You get more of a reward that way. By doing the harder thing, you will get more of a reward. Extensive frontal damage, they never, ever, ever are able to reach for the 1 M&M. They always get pulled towards the easier solution, the easier, more superficial way. There's 5 M&Ms. That's what I want. Instead of being able to do the executive stepping back and saying, if I go for 1 right now, I will get 5. What is remarkable is you get an individual with frontal damage, and they will tell you what the rule is. They will sit there and say, I know what you're up to. You want me to grab the 5, but then I'll only get 1. What I need to do is grab the, and then they go for the 5. They can verbalize the rule right there. They know the difference between right and wrong. This is not organic impairment of knowing the rules. This is organic impairment of being able to follow the rules. And it is extraordinary what this one feature of what the frontal cortex does, the difference between knowing that there's a difference and being able to activate this pathway instead of that. This is hugely, hugely challenging the courts. At the time that Hinckley attempted to kill Reagan, every single state in the country had a McNaughton ruling in place. Yeah?
So for those people that just have the damage and know the rules, would they cover up their tracks in the court case so they would be deemed not worthy of the McNaughton rule?
Okay. They would fail the McNaughton ruling, absolutely, because they know the difference between right and wrong. And
they would carry out the action and realizing it was wrong, so try and hide it.
Yeah, exactly. Or if they're disturbed enough, okay, for our purposes, yes, the person will know the difference between right and wrong, but they still cannot regulate their behavior. And this is a huge problem. What you wind up seeing is the McNaughton rule has generally been accepted in most states in this country. At the time that Reagan, the assassination attempt was made, federal criminal rulings had McNaughton ruling in it. Almost all the states had McNaughton, and something about 10 or 11 of them also had an organic impairment of volitional control, recognizing realms of frontal damage. And what was very interesting was in the aftermath of Hinckley being found criminally insane instead of guilty, there were these Neanderthal bellowings all over the country, editorials everywhere about how Hinckley had gotten away with it. Within a month, the federal government, Congress, revoked the ability to have a McNaughton ruling in any federal criminal trial. The vast majority of states in this country, their legislatures promptly leapt into action to repeal McNaughton. And along the way, I think in all but 1 or 2 states, the volitional impairment rulings went down the tubes also. And at this point, the vast majority of states in this country, you could have your frontal cortex blown out of the water and you've got 1/2 neuron still functioning there, and that is not relevant in a court of law. An area that desperately, desperately needs some reform. To give you a sense of how bizarre this could look, this dissociation here between knowing the difference between right and wrong and being able to regulate your behavior, this is what it would look like in terms of criminal sort of behavior with frontal cortical damage. And bizarrely, this was actually a law case I was involved with some years ago, where this was an individual who had just been convicted of his 8th and 9th murders. And this was a serial murderer, and he was like a nightmare beyond imagination, what this man was. And this 8th and 9th one had just been 2 boys he had abducted, kept captive for a week, sexually raped, sexually mutilated, and strangled. And this was number 8 and 9. And he had been brought out of a maximum security prison in Florida where he was serving a whole bunch of other life sentences. And this was a case down in San Diego that he was brought out for that one. And the defense consisted of 3 minutes of the defense attorneys getting up and saying, yes, he did it. He absolutely did it. This was the defense. So this was now in the penalty phase, deciding, was this person going to get the death penalty, or was he going to get life in prison without the chance for parole? And the relevant thing about him was, when he was 6 years old, he had had a massive car accident that destroyed his frontal cortex. He spent 2 months in a coma, no prior history of antisocial behavior, no family history of any of it, came out of it extremely behaviorally disinhibited. By age 11, he had assaulted his first individual, first murder by age 13, a completely broken machine. Here's what behavior looks like in somebody with no frontal cortex in this realm. One of the things he also did, in addition to a string of murders, were kidnapping and rape and aggravated assault. And this was one woman who had managed to fortunately survive this. And she'd been abducted by him, where he took her to his apartment and kept her there for a week, repeatedly raping her, beating her senseless, days and days of this going on. And eventually, whatever it is that shifted in him shifted. He had, of course, her wallet in the process of kidnapping her and seeing her name, where she lived. He finally says, okay, time to go, bundles her into his car and drives her home. And as he lets her out, he says, I had a really good time. I hope you did too. Here's my phone number. Maybe we can get together again sometime. And drives away. And no surprise, he was arrested within an hour or so and eventually sort of pinned to a whole bunch of these other ones. This is what it looks like when you got no frontal cortex. What's interesting there is obviously making no attempt to cover his tracks, he was able to verbalize some of these rules and say it was inappropriate, and he was able even to be told the specifics of his own case with other names used and be able to say, whoa, that's not something you should do, that's against the law. At these junctures, though, completely going off the rails. He had an interesting combination, though, which is that there were some elements of the difference between right and wrong aspect of it. The fact that he had his frontal cortex damaged so early in life, what you tend to see is around age 5 or 6 or younger, the person tends to never quite incorporate the rules either. It's not till you get, say, adults who get frontal damage that you get the absolutely pure dissociation between this is not okay to do, this is a wrong thing to do, I am not going to do it, and then goes and does it. He instead had this much more mixed case there. When you get the frontal damage around ages 5 or 6 or younger, you get what is now termed acquired sociopathy. You don't do a great job of incorporating